Welcome! In today's session, we'll be tackling LeetCode problem number 1537, get the maximum score. This problem challenges us to find the maximum score by traversing two arrays strategically. We'll explore various approaches, analyze their efficiencies, and work toward an optimal solution. Let's dive in. In this problem, you're given two sorted arrays, nums1 and nums2, and your goal is to find the maximum score you can achieve by traversing these arrays under specific rules. You can begin at any index in either array, and from there, you can either move to the next index in the same array or jump to the same index in the other array, but only if the values at those indices are equal. The traversal ends as soon as you reach the end of one array, and your score is calculated by summing all the elements you pick during the traversal. Because the score might be large, you'll return the result modulo 10 to the power of 9 plus 7. The input consists of two integer arrays, and the output is a single integer representing the maximum score. Let's walk through some examples to better understand these rules. Consider the first example, where nums1 is 2, 4, 5, 8, 10, and nums2 is 4, 6, 8, 9. The output is 30. Here's how we achieve it. Start at index 0 of nums1 and pick the value 2. Then, move to the next value, 4, which is common to both arrays. At this point, you can jump to nums2. From there, pick 6 and continue to 8, which is another common value, allowing you to jump back to nums1. Finally, pick 10 from nums1 to complete the traversal. The total score is 2 plus 4 plus 6 plus 8 plus 10, which equals 30. This example illustrates how jumping between arrays at common values can help maximize the score. Now let's look at the second example. Here, nums1 is 1, 3, 5, 7, 9, and nums2 is 3, 5, 100, and the output is 109. Starting at index 0 of nums1, pick the value 1. Then, move to 3, which is a common value, and jump to nums2. From nums2, pick 5, another common value, and continue in nums2 to pick 100. Your total score is 1 plus 3 plus 5 plus 100, which equals 109. This example highlights how identifying and leveraging common values between the two arrays can lead to an optimal path. In the third example, nums1 is 1, 2, 3, 4, 5, and nums2 is 6, 7, 8, 9, 10. The output is 40. Here, there are no common elements between the two arrays, so the best strategy is to simply pick all elements from the larger array. By summing the elements in nums2, which are 6, 7, 8, 9, and 10, you get a score of 40. Alternatively, if you chose nums1, the score would be 15, which is smaller. This demonstrates that when there are no overlaps, the solution is to take the array with the larger sum. Finally, let's discuss the constraints and key observations. The lengths of nums1 and nums2 can go up to 10 to the power of 5, and the values in the arrays can be as large as 10 to the power of 7. This means the solution needs to be efficient and able to handle large inputs. A critical observation is that at each common element, you face a choice: either continue in the current array or jump to the other array. To solve this efficiently, you can use dynamic programming or a two-pointer approach to calculate the maximum score while minimizing unnecessary computations. By carefully managing these transitions, you can ensure an optimal solution within the constraints provided. To begin, the brute force approach relies on the intuition of exploring all possible paths to maximize the score. Since the goal is to traverse two arrays and switch between them at common elements, the naive strategy involves considering every potential path. Specifically, we start from the first element of both arrays and calculate scores for each possible sequence of switches at intersection points. At each switch, we compute the sum of the subarrays up to that point, choose the maximum, and continue. However, this approach has a significant drawback: the number of paths grows exponentially with the number of intersections. This results in a time complexity of O2 to the power of k, where k is the number of common elements, making it computationally infeasible for large inputs. Therefore, while conceptually simple, this method is not a practical solution for this problem. Now, a more efficient solution is the optimized approach using two pointers. This method leverages the fact that the arrays are already sorted, allowing us to traverse them simultaneously in linear time. The key insight here is that we can use two pointers, one for each array, to efficiently manage the traversal. As we iterate, we maintain two running sums, one for each array, to keep track of the accumulated scores. If the current element of the first array is smaller, we add it to its running sum and move its pointer. If the current element of the second array is smaller, we do the same for the second array. When we encounter a common element, we take the maximum of the two running sums, add the common value, and reset both sums. After completing the traversal, any remaining elements in either array are added to their respective sums, and the maximum of the two totals is returned. This approach is highly efficient with a time complexity of O, m plus n, where m and n are the lengths of the arrays. Its simplicity, reliance on the sorted property, and avoidance of redundant calculations make it an excellent choice for solving this problem. The two-pointer approach was chosen based on several key observations. First, the essence of the problem is to combine two sorted arrays in a way that maximizes the score. The presence of common elements simplifies this process, as they serve as natural points for switching between the arrays. By maintaining running sums for both arrays and always taking the maximum score at intersections, we ensure an optimal solution. This approach is efficient, with a linear time complexity that makes it suitable for large input sizes. Additionally, it is straightforward to implement, with clear modular steps that enhance both clarity and debuggability. While alternatives such as dynamic programming could be considered, they add unnecessary space complexity without improving time efficiency. On the other hand, the brute force approach, although conceptually simple, is impractical due to its exponential time complexity. The two-pointer strategy strikes the perfect balance between simplicity, efficiency, and correctness, making it the optimal choice for this problem. To solve this problem, we need to determine the maximum score that can be achieved by traversing two arrays, nums1 and nums2. The traversal can begin at the start of either array, and we accumulate the sum of elements as we move along the chosen path. The twist lies in the intersections, points where the two arrays share a common element. At these intersections, we have the option to switch to the other array or continue with the same one. Our goal is to maximize the total sum by making optimal decisions at each step. One way to approach this problem is with brute force. The intuition here is simple: examine all possible paths by considering every possible combination of switching decisions at the intersections. First, we identify all the common elements between the two arrays, which serve as potential switching points. Then, for each combination of these decisions, we traverse the arrays, calculate the sum for the chosen path, and track the highest sum encountered. While this method ensures that we evaluate every possibility, it becomes computationally impractical as the number of intersections grows. This is because the number of paths to explore grows exponentially with the number of intersections, leading to a time complexity of O2 to the power of m asterisk n, where m is the number of intersections and n is the array length. Clearly, a more efficient approach is needed. A more efficient solution involves using dynamic programming with two pointers to eliminate the need to explore all paths. The key idea is to keep track of the maximum score achievable up to each index in both arrays. By leveraging dynamic programming, we can focus on optimal subproblems and avoid redundant calculations. Here's how it works: we start by initializing two variables, score1 and score2, to 0. These will represent the maximum scores accumulated so far in nums1 and nums2, respectively. Using two pointers, I and j, we traverse nums1 and nums2. If the current element in nums1 is less than the current element in nums2, we add that value to score1 and move the pointer I forward. If the element in nums2 is smaller, we do the same for score2 and move j forward. When we encounter an intersection where nums1, I, equals nums2, j, we update both scores to the maximum of the two scores plus the value of the common element. Then, we move both pointers forward. After one of the pointers reaches the end of its array, we simply add the remaining elements of the other array to its respective score. Finally, we return the greater of the two scores, score1 or score2. This approach is highly efficient, with a time complexity of O, n plus m, where n and m are the lengths of the two arrays, and it requires only constant space. To solve this problem efficiently, there are a few key insights to keep in mind. First, the critical decision points are the intersections between the two arrays. These are the only places we need to consider switching paths, as every other step is straightforward addition in one of the arrays. Second, the dynamic programming transition at each intersection is based on the maximum score attainable from either array up to that point. By focusing only on these optimal scores, we avoid the need to explore every possible path. Lastly, the two-pointer technique is central to traversing the arrays efficiently. It allows us to process both arrays in linear time while dynamically updating the scores. In terms of data structures, we use two pointers to traverse the arrays and two scalar variables, score1 and score2, to store the maximum scores for nums1 and nums2. This keeps the space complexity minimal. It's also important to handle a few edge cases. For instance, if there are no intersections, the best solution is simply the sum of the longer array. If one or both arrays are empty, the result is 0. Lastly, for single-element arrays with one common value, the maximum score is just the value of that element. These considerations ensure that the algorithm is robust and handles all possible input scenarios. Let's walk through an example to see the algorithm in action. Suppose nums1 is 2, 4, 5, 8, 10, and nums2 is 4, 6, 8, 9. We start by initializing score1 and score2 to 0, and the two pointers, I and j, to the beginning of their respective arrays. First, nums1, 0, is 2, which is less than nums2, 0, which is 4. So, we add 2 to score1 and move pointer I forward. Now, nums1, 1, equals nums2, 0, both being 4. This is an intersection, so we update both scores to the maximum of the two scores plus 4, resulting in a value of 6. Then, we move both pointers forward. Next, nums1, 2, is 5, which is less than nums2, 1, which is 6. We add 5 to score1 and move I forward. Then, nums1, 3, equals nums2, 2, both being 8. Again, this is an intersection, so we update the scores to the maximum of the two scores plus 8, resulting in 19. Both pointers move forward. Finally, we process the remaining values, adding them to their respective scores. At the end, score1 is 30 and score2 is 29. The result is the maximum of these two values, which is 30. This demonstrates how the algorithm efficiently calculates the maximum score by leveraging dynamic programming and two pointers. This implementation solves the LeetCode problem number 1537, get the maximum score efficiently by using a two-pointer approach. Here's a detailed explanation of the code. 1. Initialization. The function starts by defining a constant mod, 10 to the power of 9 plus 7, to handle the modulo operation for large sums. We also initialize pointers I and j to traverse nums1 and nums2, respectively. Sum1 and sum2 are used to track cumulative sums along the two arrays, while result stores the final maximum score. 2. Main loop. The while loop continues until both pointers have traversed their respective arrays. The key logic within the loop determines whether to advance in nums1, nums2, or both. If the current element in nums1 is smaller, we add it to sum1 and move the pointer I forward. If the current element in nums2 is smaller, we add it to sum2 and move the pointer j forward. If the elements are equal, we encounter an intersection. At this point, the maximum of sum1 and sum2 is added to result, along with the current intersection value. Both sums are reset, and both pointers are increment. 3. Final adjustment. After exiting the loop, there might still be some residual sums in sum1 or sum2. We add the larger of these to result to account for the remaining path. For modulo operation, the final result is returned modulo 10 to the power of 9 plus 7 to ensure it fits within the problem's constraints. This approach ensures an optimal solution by leveraging the sorted nature of the input arrays and avoids unnecessary recomputations, achieving a time complexity of O(n plus m). The use of two pointers ensures that both arrays are traversed in a single pass, making the algorithm efficient and elegant. In this implementation, we start by importing the necessary libraries and defining our class and method. The goal of this method is to calculate the maximum score by traversing through two sorted arrays, nums1 and nums2. To handle the large numbers, we define a constant mod set to 10 to the power of 9 plus 7, which will be used later to keep the result within bounds. We also initialize variables. N and m store the lengths of nums1 and nums2, respectively, while I and j will act as pointers for iterating through the arrays. Additionally, we set up sum1 and sum2 to accumulate sums along each array path, and result to keep track of the maximum score. The while loop forms the core of the algorithm, running as long as there are elements left in either array. Within the loop, we compare elements at the current pointers. If the current value in nums1 is smaller, we add it to sum1 and advance the pointer I. Similarly, if the value in nums2 is smaller, we add it to sum2 and move j. When the elements at both pointers are equal, this marks an intersection point. Here, we add the greater of the two sums, sum1 or sum2, to the result, along with the common value at the intersection. Then, we reset both sums to 0 and advance both pointers to continue exploring further. Finally, after exiting the loop, we add the maximum of the remaining sums, sum1 or sum2, to the result. This ensures that any leftover elements from either array are accounted for in the score. The result is then returned as an integer after taking the modulo with mod. This ensures the result fits within the required limits and avoids overflow issues. Overall, this implementation efficiently calculates the maximum score by leveraging the sorted property of the arrays and using a two-pointer approach to traverse them simultaneously. To begin solving the problem, we are given two arrays, nums1 is 2, 4, 5, 8, 10, and nums2 is 4, 6, 8, 9. We initialize pointers I and j at 0 for both arrays, and set sum1, sum2, and result to 0. Now, as we compare elements from the two arrays, the process unfolds as follows. The first element of nums1, 2, is less than the first element of nums2, 4, therefore, we add 2 to sum1, updating sum1 to 2, and move the pointer I to the next position. Then, we encounter a match where nums1, I, and nums2, j, both equal 4. Here, we add the maximum of sum1 and sum2, which is max, 2, 0, along with the common element, 4, to the result. This brings the result to 6, and we reset both sums to 0. The pointers I and j are then increment to 2 and 1, respectively. Next, since nums2, j, equals 6, which is greater than nums1, I, at 5, we add nums2, j, to sum2, making sum2 equal to 6, and increment j to 2. Then, as nums1, I, at 5 is less than nums2, j, at 8, we add nums1, I, to sum1, updating sum1 to 5, and move I to the next position. Finally, when nums1, I, and nums2, j, both equal 8, we again add the maximum of sum1 and sum2, which is max, 5, 6, plus the common element, 8, to the result, resetting both sums to 0 once more. At this point, the result increases to 20. We then increment both pointers, setting I to 4 and j to 3. Now, nums2, j, equals 9, which is less than nums1, I, at 10. Therefore, we add nums2, j, to sum2, updating sum2 to 9, and move j to the next position. Since nums2 is now exhausted, we add the remaining value in nums1, which is 10, to sum1. This updates sum1 to 10, and I is increment to 5. Finally, with both arrays exhausted, we add the maximum of sum1 and sum2, which is max, 10, 9, to the result. This brings the result to 30. The final output for this example is 30. In the next example, we are given nums1 is 1, 3, 5, 7, 9, and nums2 is 3, 5, 7, 9. Once again, we initialize I, j, sum1, sum2, and result all to 0. Starting with the first elements, nums1, I, equals 1, which is less than nums2, j, at 3. So, we add 1 to sum1, updating sum1 to 1, and increment I to 1. Now, nums1, I, and nums2, j, both equal 3. At this juncture, we add max, sum1, sum2, which is max, 1, 0, plus the common element, 3, to the result. This updates the result to 4, and we reset both sums to 0. Both pointers are increment, with I set to 2 and j to 1. The next elements, nums1, I, and nums2, j, both equal 5. Again, we add max, sum1, sum2, plus nums1, I, to the result, which updates the result to 9. The sums are reset, and the pointers move forward. Similarly, at the next step, nums1, I, and nums2, j, both equal 7. We add max, sum1, sum2, which is 0, plus 7 to the result, making it 16, and reset the sums once again. Now, I is increment to 4 and j to 3. At this position, nums1, I, and nums2, j, both equal 9. We add max, sum1, sum2, which is 0, plus 9 to the result. This brings the result to 25. The sums are reset, and both pointers are increment, with I set to 5 and j to 4. With both arrays now exhausted, we add the maximum of the remaining sums, which is max 0, 0, to the result. This leaves the result unchanged at 25. The final output for this example is 25. The time complexity of this solution is O, n plus m, where n is the length of nums1 and m is the length of nums2. This is achieved through efficient traversal of the arrays using two pointers. Both pointers, I and j, iterate through nums1 and nums2 respectively, ensuring that each element is processed at most once. In the worst-case scenario, this results in a total of n plus m iterations. During these iterations, the algorithm performs constant time comparison operations to decide whether to advance a pointer or handle an intersection. Since these comparisons happen once per iteration, their total cost also scales linearly with n plus m. Additionally, the arithmetic operations, such as additions and assignments, are constant time and do not contribute further to the overall complexity. This systematic traversal ensures that the time complexity remains linear, proportional to the total number of elements in both arrays. With all operations bounded by the traversal of the arrays, the overall time complexity is O, n plus m. Now, when it comes to space complexity, the solution is highly efficient, requiring only O1 additional space. This is because the algorithm uses a fixed number of variables, including the two pointers I and j, and auxiliary variables like sum1, sum2, result, and mod for intermediate calculations. These variables occupy constant space irrespective of the input size. Furthermore, no additional data structures, such as lists or dictionaries, are created, and the input arrays nums1 and nums2 are accessed without modification. In summary, the space complexity remains constant, making the solution not only time efficient but also memory efficient. To better understand the efficiency of this solution, let's compare it to a naive approach. A brute force method would involve exploring all possible paths through the two arrays, calculating the sum for each path, and finding the maximum. However, this approach results in O(2) n plus m time complexity due to the exponential number of possible paths created by branching at every common element. In contrast, the optimized solution avoids this inefficiency by using two pointers and maintaining running sums for the arrays. By directly comparing elements and efficiently merging paths at intersections, the algorithm eliminates redundant computations. This reduces the time complexity drastically to O, n plus m, which is optimal given the constraints of the problem. Now let's analyze the algorithm's performance in different scenarios. In the best case, if one array is empty, the algorithm only needs to traverse the other array, resulting in a time complexity of O, max, n, m. In the average case, where both arrays contain elements with a few intersections, the time complexity remains O, n plus m, since every element is processed once. Even in the worst case, where there are multiple intersections and both arrays are fully traversed, the algorithm still operates in O, n plus m, time. This is because the two-pointer approach ensures that each element is visited exactly once, regardless of the input configuration. These characteristics make the solution robust across different input cases. Finally, let's solidify our understanding with a mathematical proof of the time complexity. Each element in nums1 and nums2 is processed exactly once during the traversal, as the two-pointer approach ensures no element is revisited. Every operation within the loop, whether it's a comparison, addition, or assignment, takes constant time. Therefore, the total work done is directly proportional to the sum of the lengths of the two arrays, leading to an overall time complexity of O, n plus m. To summarize, the solution achieves O, n plus m, time complexity and O1, space complexity, making it both optimal and significantly faster than the naive exponential time approach. This balance of efficiency in time and space makes the algorithm well-suited for handling large input sizes. One of the most common mistakes in this problem is failing to handle intersections properly. Many solutions assume that whenever arrays intersect, you should always switch to the other array to maximize the score. But that's not always true. At each intersection, you have two choices: stay on the current array or switch. To ensure the best outcome, you need to evaluate both options carefully. Techniques like dynamic programming or prefix sums can help you compare these choices efficiently. Another frequent issue is overlooking edge cases. For example, if one array is significantly shorter than the other or if the arrays have no intersections at all, your solution might fail or produce errors. To address this, test your code against a wide range of inputs, including arrays with no common elements, arrays of size 1, or even arrays with repeated values. Lastly, relying on an inefficient brute force approach is a trap many fall into. Trying to compute all possible paths can lead to exponential time complexity, which isn't feasible for larger inputs. Instead, optimize your solution using dynamic programming, prefix sums, or two-pointer techniques to bring the complexity down to O(n). Another mistake to watch out for is incorrectly accumulating scores when switching between arrays. Errors like forgetting to reset sums or combining scores incorrectly can lead to wrong results. To prevent this, maintain separate score trackers for each array and carefully merge them when you reach intersection points. Mismanaging array indexes is another common pitfall. As you traverse two arrays, keeping track of the current indexes can become tricky, especially when you switch arrays at intersections. This can result in out-of-bounds errors or incorrect calculations. Clear pointer logic is key here. Ensure that your pointers are updated properly whenever you switch, so the traversal remains accurate and efficient. This problem highlights an important pattern often seen in interviews: traversing two sorted arrays efficiently. Mastery of this pattern, which includes minimizing redundant computations, can give you an edge in similar problems. Interviewers also value solutions that balance performance and readability. Using dynamic programming where the two-pointer technique achieves both, as these approaches are optimal in terms of time complexity and easy to follow. Additionally, being able to explain the trade-offs between different approaches, such as O(n) versus O(n squared) time complexity, demonstrates a deeper understanding. Finally, pay special attention to edge cases. Clearly communicating how your solution handles challenging scenarios not only shows robustness but also reassures interviewers that your code is reliable under all conditions. If you're looking to practice related problems, there are several excellent options. For instance, LeetCode 121, Best Time to Buy and Sell Stock, focuses on maximizing profit through simple traversal and comparison logic. LeetCode 122, Best Time to Buy and Sell Stock 2, builds on this by introducing multiple transactions, resembling the strategic path selection in this problem. Another great exercise is LeetCode 1091, Shortest Path in Binary Matrix, which involves optimizing paths while managing states effectively. LeetCode 42, Trapping Rainwater, uses a two-pointer approach for efficient accumulation, similar to the techniques here. Lastly, LeetCode 1753, Maximum Score from Removing Stones, shares the goal of maximizing scores under constraints, making it a great extension of the concepts explored in this problem. Great job! To wrap up, we reviewed how to get the maximum score using an optimized two-pointer approach. This problem underscores the importance of efficient traversals and strategic thinking. Keep practicing, and we'll see you in the next session. Thank you. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!